We're in forecasting, and this is going to be my part 3 for Module 9. And we're going to start talking about steering winds and specifically looking at above the United States within the Ferrel cell. I have a natural wind current that is flowing westerly. So going back to our cells again, at the equator, going to about 30. So my low pressure at the equator where air is rising up, it's diverging aloft. So the air above is diverging aloft, and then it's moving out across. As I move out across, the air begins to curve because the Coriolis effect takes effect. And that air that's curving at the equatorial belt actually curves easterly. So it goes from the east towards the west. It will run out of energy and cool off and have its little location, and it will sink down, and it does that right around 30 degrees-ish north latitude and 30 degrees south latitude, and those end my Hadley cell. At that high pressure, where that area has sinking air, that high pressure system begins my Ferrel cell, which is my mid-latitude cell and the one that we're watching here. That air is on the surface of the earth, and it's diverging on the surface of the earth, and it comes under the influence of the Coriolis force, and so it bends, and it gets pulled in a westerly direction. That air does warm up, and it does rise, and it tends to have a nice rising center somewhere between 60, 50 degrees north latitude, and so it will rise up in those locations. And I have a nice low pressure center, and that low pressure center is my polar front, and it's also the end of my Ferrel cell. And then finally is my polar cell, where the air at that 50, 60 degree mark, that is the low pressure, is rising up, and it diverges. It gets pulled easterly, so it moves from the east to the west, and it sinks around the pole itself. So that's just reviewing my cell cycles. So I'm in my Ferrel cell with my westerly winds, which is what they're named after, westerlies, and I can see that my natural wind currents are occurring. And then in this example, I can see I have a building trough and a building ridge forming a Rossby wave. And these are wind currents that also have a certain amount of energy behind them, which has to do with where they're coming from. Once again, I'm naming them for where they're coming from, but we call them steering winds. And these steering winds come in two different names over the United States and Canada. And one is called the Alberta Clipper, and that's because the zone that it's coming out of is Alberta, Canada. And the other one is called the Colorado Low, and that's because the zone is coming off of the Colorado Rockies and their mountains. So here we go. Here's our Alberta Clipper and its steering direction, and it's Colorado Low and its steering direction with my natural wind currents. But notice they're both westerlies, named for where the wind is coming from. It's coming from the west and going to the east. Just defining different maps and steering direction and wind currents. A lot of this is terms, but here we go. Here's the migration of the surface winds, and we can see my trough forming and my ridge forming. And right along that trough, the air within my jet stream is flowing. It is in this low pressure center picking up more air because the air is rising up on the surface, and it's feeding into my steering winds, which also means that my storm is going to steer with the steering winds, hence the word steering winds, right? They're going to move with this natural jet stream. This jet stream is going to pull the air aloft, which is going to move the surface storm because this is the cloud mass that's going to go with this air current. Once again, this is my open wave or my mature occlusionary stage along the low pressure center, which means air is spinning in a counterclockwise direction in the northern hemisphere, and the air is moving on the surface in towards the low pressure gradient force, rising up and diverging aloft. And in this case, because it has a steering wind and a jet stream, it's diverging and getting pulled in the westerly winds. So it's going out in this direction. This little picture is just showing you where it's steering to. So it's going like this and going up. Which brings me to the conveyor belt. conveyor belt model basically shows that as the air moves up, it will actually spin, and its vortice of spin is so clean in its rotation. I have a natural kind of rotational conveyor belt of air mass rising up along my low pressure center. And this just goes through what is a warm, what is a cold, what is a dry conveyor belt. But this is what it looks like. So this is what I'm trying to get you to see. And so here is a warm conveyor belt occurring. Here is my dry conveyor belt occurring. And here is my cold conveyor belt occurring, which is sort of in the back. And it shouldn't be over here. It should actually be kind of along this front line and feeding in and spinning up. They're all rotating in the same direction. They're all rotating so that when they rotate up, they happen to be spinning around at different heights of altitude, right, as they go up. And each one is feeding into the main part of the storm low pressure. So notice this lovely line. This would be my low pressure back here on the surface, right? So that's the low pressure storm. This is my warm front here. And so this is my warm air feeding up and into that low pressure center. This is my cold air, which is feeding up into the low pressure center, but the rotation is deceiving. It should be over here in the cold. I'm sorry. And then the dry is kind of feeding up and over the cold. So it's back here, but they're all feeding into that same steering wind and low pressure center because everything is moving with pressure gradient force. It is moving from high pressure systems to low pressure systems. So it's all moving in towards that low pressure on its conveyor belt. Anticyclones, we've talked about that, is a rotational air around the high, surface high. So on the surface of the earth, surface high. And that means that the air in this location is sinking down on the high pressure and it's diverging on the surface, which means that the place directly underneath where the high pressure is going to have clear skies and no breezes. It is calm and clear in these locations. And there are places in the world which have persistent high pressures. This is around 30 degrees, and one of the examples is Santa Ana region, also known as our Mojave Desert in the United States. So talking a little bit about climate change and mid-latitude cyclones, according to the IPCC, which is the International Policy for Climate Change, their group and all of the research that's been working on what's going on has noticed a drastic increase in mid-latitude cyclones. They've also noticed a drastic increase in the severity of those cyclones. So when they occur, they tend to be stronger, and that is because there is more energy in the atmosphere at this current time. Because of the increase in the number of fossil fuels, the atmosphere itself has the capacity to hold more heat, and therefore there's more energy to go around. So it can be transferred to bigger, stronger wind conditions, i.e. faster wind speeds, faster rates of rise, and more capacity for moisture, right? So these are all things that are coinciding with climate change that are directly caused by the increase in the number of fossil fuels in the atmosphere. What that means is that we will continue to see in the future mid-latitude cyclone storm events that will persist into seasons that they're not as commonly heard of. For example, mid-latitude cyclones that turn into nor'easter-like events, so things that have strong wind conditions, strong snow conditions, and rotational conditions that we associate with winter will persist into the spring months, like March. We will see them as they persist into those, and we will also see the potential for them to begin to occur earlier in the seasons themselves. Also, when they happen, they will pack a greater punch. They will have more energy, and therefore they will be able to produce greater amounts of snow, and they will have faster wind speeds. And even in the last 15 years, we've seen mid-latitude cyclones increase their wind speeds to those that rival hurricanes now. And we'll continue to see that as the future comes about. So on those notes, that's a little bit about what we can expect due to global climate change. And as always, if you have any questions, comments, concerns, please post inside the chapter discussion. And I'll see you next module.